All right, everyone, we've been talking a lot about the cross product and different ways to compute it, but we haven't looked at an example yet together. Now let's go ahead and do that. So in this example, we're finally going to evaluate a cross product using the components of two vectors. So we're going to evaluate A cross B, given that our first vector A has components of 1, 3, and 4, and our second vector has components of 2, 7, and -5. And I'm going to go ahead and use that order 3 determinant approach to evaluating our cross product. So let's go ahead and set everything up. We're looking at A cross B, which we can represent using this order 3 determinant. Remember, the first row of our determinant are our basis vectors I, j, and k. They're basically placeholders. The next row in our order 3 determinant are going to be the entries of our first vector A. So that'll be 1, 3, and 4. And our third row will just be the corresponding entries for our second vector B. And those entries are 2, 7, and -5. All right, so in order to evaluate this cross product very quickly, we can just use that right and left diagonal technique that I mentioned earlier. And so we can start with our I components. If we go down our right diagonal, we're going to have 3 times -5, which will give us -15. And we have to subtract away from that the product of the left diagonal starting at I. And that'll give us, after wrapping around, 4 times 7, or 28, that we have to subtract from -15. So our I component is going to be -15 minus 28. Next, we have to look at our J component. And so we start at J, and we move down the right diagonal, and that'll give us 4 times, after wrapping around, 2. 4 times 2 will give us 8. And then we just have to subtract away from 8 the left diagonal that starts at J, and going to the left, that'll give us a factor of 1. And then going down to the left again and wrapping around will give us a second factor of -5. So we're subtracting 1 times -5, or we're subtracting a -5 away from 8, and that'll give us our jth component. And so now to finish this off, we have to find our kth component. And for that, we're going to start at k and move down the right diagonal. That'll cause us to wrap around right away. That right diagonal will give us 1 times 7, or 7. And we have to subtract away from that the left diagonal that starts at k. And that left diagonal will involve a factor of 3 and a factor of 2. And so that'll give us a 6 that we have to subtract away from that first piece. And so now we've done our right minus left diagonals for each piece or component. Now we just have to simplify, and we will have the output of our cross product. So what is -15 minus 28? Looks like -43. What is 8 minus -5? That's +13. And what is 7 minus 6? That is 1. So our end result, the output of this cross product, is going to be -43i plus 13j plus k. And so there was no physical context to this question or cross product that we just evaluated. But if we did want to try to geometrically interpret this vector, what we could say about this vector that came out of our cross product is that this vector of -43i plus 13j plus k is going to be orthogonal or perpendicular to both our vectors A and B. If we took the dot product between A and this vector, as well as the dot product between B and this vector out of our cross product, we should get 0 for both of them. Because remember, if the dot product between two vectors is 0, those two vectors are perpendicular or orthogonal. In this next example, we are asked to find the vector that is orthogonal or perpendicular to the plane that is determined by the 3 given points. Our first point is called P, and it has x, y, and z coordinates of 1, 4, 6. The second point is Q with coordinates of -2, 5, -1. And our final point is R, and its coordinates are 1, -1, and 1. So we will be talking a lot more about lines and planes coming up soon, and the cross product is going to be a really important tool when we are working with these concepts. And so this exercise is a little bit of a glimpse or a sneak preview of some of the work we're going to be doing pretty soon in our course. And so the idea is, if we have 3 points, P, Q, and R, those 3 points floating around in three-dimensional space are going to form a plane. And so we can think of a plane as an infinitely long, flat piece of paper. And what's kind of special about planes is they're going to be uniquely determined by a single orthogonal vector. If you go to any point in the plane and look at a normal vector to that plane, or a orthogonal or perpendicular vector, they're all going to point in either the same direction or the same but opposite direction. Being able to find this vector that is orthogonal or perpendicular to a plane is really important in later finding the equation for that plane. So if we have two vectors that actually lie within our three-dimensional plane, then we can find the vector that is orthogonal to our plane by finding a vector that is orthogonal to those two vectors within our plane. But the cross product does exactly that. Given two vectors, it finds a vector that is orthogonal to both. So with the given information and these 3 points, we have to start by finding two vectors that lie within our plane and are not parallel to each other. So one of those vectors could be the vector that goes from P to Q, and another one could be a vector that goes from P to R. So how do we find the vector that starts at P and goes to Q? Well, we just take the difference between the components of our two vectors to find this position or displacement vector that goes from P to Q. So -2 minus 1 will give us our first component, and that will be -3. Our second component will be 5 minus 4, which is 1, and our final component will be -1 minus 6, which is -7. So our first vector in our plane, we can call it A, but it's really just the vector that goes from P to Q, those 2 points in our plane. And so for our second vector in our plane, we'll call it B, and we'll create our second vector B by creating the vector in our plane that goes from P to R. So the ending point of this vector is R, and the starting point is P. So to create that vector between our 2 points, we just take the difference between the final point and the initial point. And so that vector will have a first entry of 1 minus 1 or 0, a second entry of -1 minus 4, which is -5, and a third entry of 1 minus 6, which is also -5. And so now A and B are two vectors within our plane. And now if we take the cross product between those two vectors, we'll get our vector that is orthogonal to both of those vectors and orthogonal to our entire plane spanned by these 3 points and those two vectors. So really now all it comes down to is evaluating A cross B, and we can evaluate this cross product using our order 3 determinant. So remember, the first row in our setup using an order 3 determinant are our basis unit vectors I, J, and K. Our second row is going to be the entries of our first vector, A, which is -3, 1, and -7. And our second vector, B, goes in that third and final row. So that third row will be the corresponding entries of 0, -5, and -5. So now we just need to evaluate or simplify this order 3 determinant, and then we will have our vector that is orthogonal to the plane determined by the 3 given points. So remember, we can use our right and left diagonals. And so our right diagonal from I is going to be 1 times -5. So that'll be -5. And then we have to subtract away from that the left diagonal that starts at I. And so that'll be -7 times -5, which is +35. But we're subtracting that +35. And that'll finish building the ith component of this vector. Up next, we move to the jth component. So its right diagonal, including that wraparound, will look like -7 times 0. But that is going to be 0. Then we have to subtract away from that the left diagonal that starts at J. So it'll be J, a -3, wrapping around and hitting that -5. So we have to subtract -3 times -5, or subtract a +15 to create our jth component. Then to finish this off, we need our kth component. And so again, we start at K and go down our right diagonal, which will give us -3 times -5, or a +15. then we have to subtract away from that the left diagonal that starts at k, and that left diagonal will give us a product of 1 and 0, or just a 0. So now putting this all together and just simplifying by combining some of these constant numbers together, it looks like our final answer is going to be negative 40i minus 15j plus 15k. That is going to be our vector that is orthogonal to the plane determined by the 3 points given, P, Q, and R. So technically this is not the only vector that is orthogonal to the plane determined by these 3 points, but any other vector that is orthogonal to our plane is going to be parallel to this vector. So it'll point in the same direction but be of a different size or magnitude, or it could point in the negative or opposite direction and also be of a different size or magnitude.